Okay, let's get started. Please check your attendance of the report because today it's extremely cold today, but you are here. So do not forget checking your attendance. Okay, so as you know, so I posted lab, lab assignment. This is the final lab assignment. Okay. So actually, in this lab assignment, you are required to design a pipeline processor, right? So actually, I briefly explain about the design process for this lab, this lab. Okay, so when we learn about actually in the previous class, I explained. So we can start from the single cycle processor design, right? So it's also the same. So actually, in the sixth lab, so you need to design the pipeline processor. But you can start from the single cycle processor design, right? So what are required? What is required for designing pipeline processor? So firstly, so this is the architecture of a single cycle processor, right? So, and then we split up the steps. The required steps for executing instructions into 5 stages. Okay, so we learn the 5 stages pipeline processor, right? So what is required? We need to insert pipeline registers between between stages, right? We need to insert the instruction fetch ID pipeline register between ID and instruction fetch and ID stages. Okay. So as I mentioned, so we can start from the single cycle processor design, and we need to insert pipeline registers. Okay. Then, so actually, this is the this is the design you need to. This is the pipeline architecture you need to design in this lab assignment. Okay. So after that, so we learn how to design data forwarding unit, right? Data forwarding path and parallel detection unit. Also, we learn how to design how to handle control hazard, right? And then, as I mentioned, if we just follow the pipeline architecture in the textbook, then it is more complex, right? And then I don't think it's good design, right? Because the data cannot be forwarded for branch instructions, right? So actually, in this lab assignment, so branch unit. So this is the branch unit. So it just compares the 2 register values, right? And then, as you can see, this branch unit is located after the data forwarding multiplexers. Okay. So which means that the data can be forwarded to branch unit. Okay. So if the branch is taken, then the penalty is the 2 cycles. And then if the branch is not taken, then there is no penalty. Okay. So this is the pipeline architecture you need to design. Okay. So let's start from the pipeline register design. Okay. So for this design, actually, you need to use some new data structure or new data type of system variable. So as you can see, so this is the struct packed. Actually, it's very similar to the structure of C or C++. Okay, so they actually the structure. So in this text structure, so we can include the multiple elements. Like in this example, so as you can see, this is the type instruction fetch and ID type, right? So it means that we will use this type of implementing instruction fetch slash ID pipeline register, right? So, and then we can observe this structure, this text structure type includes two elements, two member variable. Okay, so PC and instruction. Why? So, so so this is as you can see. So this is the instruction fetch and ID pipeline register, right? And then what are input signals for this pipeline register? So as you can see, this pipeline register receives PC, right? This is here. And the output from instruction memory, so which is instruction, right? So in this data type, there are two member variables, that's the member elements. This is the HDL, right? So the PC is here, and then instruction is here. The PC and instruction. Okay. So, and then I define the name of this pipeline register as ID. So this is because, so as I mentioned, the pipeline register is just the group of D flip-flops. Okay, so what is the D flip-flop? D flip-flop is like this, it's a clock. So, and then this is D, and then this is Q. So which means, so D is the input, and then Q is the output. That at the rising edge of clock, the input signal is sampled and then transferred to the output, right? So actually, so the output of this pipeline register is the signals of in ID stage, right? So like this is the output of pipeline register, right? So actually this is the ID.PC. So it means the program counter value in ID stage, right? So this is the ID.inst, the instruction. Okay, we can define the signals of this pipeline register like this. Okay, so let's see the implementation. Let's see the implementation of this instruction fetch and ID pipeline register. So, as I mentioned, this is the structure data type. Okay, and then this structure includes PC and inst. So it means that this pipeline register receives PC and inst from instruction fetch stage, and then it transfers PC and samples the PC and inst to ID stage, right? And then also this pipeline register includes the flush control signal and spool control signal. So when the flush signal is required, when is the flush signal required? Why? So it means, so this is instruction fetch ID, and then so the instruction is flushed, which means that it generates the bubble to the ID stage. But when why do we need the flush instructions in the ID stage? Or why do we need to flush instruction in the instruction fetch and ID pipeline register? Control header, right? If control header is active, so it means that the instruction is incorrectly fetched, right? so which means that if the branch is taken, the instruction is incorrectly fetched. Then we need to cancel, which means that we need to flush this incorrectly fetched instruction, right? So this flush signal is activated when the branch is taken, right? So if which means that this is activated, so which means it's worked, right? So if instruction fetch flush, so which means that the instruction fetch is flushed, then ID becomes all 0, right? And if it's not stored, and then sometimes the instructions are stored in the ID stage. Correct. Data header, right? So if the former instruction is load instruction, then the following instruction is requires the result from load instruction. Then the following instruction needs to be stored in the ID stage. That's what we learned in the previous class, right? So if this instruction is stored in the ID stage, then the next instruction in the instruction fetch stage also needs to be stored. Do you understand? So sometimes it should be stored, but as you can see, if not stored, so this means the not, okay? So tilde represents not. So if instruction fetch is not stored, so because this is not, then this is normal case, right? So this is the normal case. It means normal case. So as you can see, PC current, the program counter is updated to the ID.PC, and the instruction is updated to the ID.inst. But when? So this is the positive edge of clock. So this is the deep flip-flop. So I mentioned that is if we use always on the FF, and then the always on the FF is executed at the positive edge of clock. So it's the rising edge of the clock. Then this part is executed. But as you can see, so if not press, flush it, and then also if not store, then this is the normal case. Then where is the store case? So in this statement, I define this is the flush case, right? And then this is the normal case. So which means that the instruction and PC are transferred to the ID stage. Where is the store case? The store case is not defined, but it's okay because So as you can see, the NLC not store. So which means that if this store case is is a remain case. So for this situation, I do not define any change. I do not define any changes. You follow me? So nothing. So which means that for the store case, id.pc and id.ist are not changing. So that's why I do not define any changes for store case. Okay? You understand? So this is the example. Okay? So this is the example implementation of the instruction fetch and ID pipeline register. Okay. Then in the ID stage, we can use the id.pc and id.inst data. Okay. Okay. So actually, in this lab assignment, so you need to implement the pipeline registers using the text instruction type. And then actually, if you see the skeleton code, okay, there's the skeleton code. So actually, so you can find so this is the pipeline instruction fetch and ID, then pipeline ID and execution and memory and write back. I already defined required member variables, required member elements of this text structure. So you don't need to modify this. Okay. So actually, instruction fetch and ID is very simple, but as you can see, ID and EX. So this is the pipeline register, and then this is the text structure for ID and EX pipeline register. So as you can see, we need to use the many other signals. Okay. So here is the. And then, so if you see this module, so actually you don't need to change other modules. Okay, actually for this lab assignment, you need to change only the pipeline of the CPU module. Okay, you can find the pipeline of the CPU.sv. Okay, so and then kindly I just define. So as you can see, so please read the comment from the this skeleton file. Okay. So and then kindly I just added some descriptions. As you can see, so this is the instruction fetch stage. Okay. And then so you need to fill this. Okay. And then this is the PC register. And then so you can find that. So actually we need to instantiate the instruction memory, right? And then also as you can see, this is already complete. It's a complete key. And also you can find that the next step is the instruction fetch and ID pipeline register. Okay. So actually, it's a field is field. You need to fill is, but I already showed the answers, right? But please understand how to implement this pipeline resistance. Okay. So you need to fill this, but I already showed the answers, right? And then instruction decoder stages. So please read comments. Okay. And then main control unit, and then complete the main control unit here, right? And immediate generator, branch target, and then hazard detection unit. So you need to design hazard detection unit. Okay. Also, register file needs to be instantiated, and then you need to connect the input and output ports of register file. Okay. And then after that, this is the ID EX pipeline register. And then you need to complete the ID and EX pipeline registers. Okay. So I already explained the instruction fetch and ID pipeline register. Okay. And then also for this actually so if you just compare some data test elements of this pipeline processor, then you can find that the register file is changing. So it means that actually if we just compare the instruction memory of a single cycle processor and the pipeline processor, then instruction memory is the same. So, but only the register file is changing. Okay, but don't worry about that. I already complete the register file module. Okay, but I want you to understand some internal coding of the register file. So what is the internal coding? So actually, when I explained about the data probing, so data probing can be done from the data can be forwarded from the memory stage to the execution, that is the input of ALU, right? Also, the write back data can be forwarded to the execution stage. That means the input of ALU. And then I also mentioned that when the data is being written back to the register file, this data can be forwarded inside of the register file. Okay. So this is called the internal forwarding. Okay. So within the same clock cycle, the written data can be transferred to the data output ports in register file. This is the internal forwarding. So when I explained about the data forwarding path in the pipeline processor, then I also mentioned that the write back data can be forwarded inside of the register file. So this is the internal forwarding. So which means that in the single cycle processor, the internal forwarding is not supported. So we don't need to support internal forwarding. So that there is no data hazard in the single cycle processor, right? But in the pipeline processor, then the register file needs to support internal forwarding. Okay. So if you read the register file module, okay, then you can find that this part and internal forwarding is already implemented. Okay, so as you can see, it's regularized. And RS1 is equal to RD, and what is this one? is a RD in. So which means that the white data, the updated data is forwarded when it's the red line, and then RS1 is equal to RD. Then the data is forwarded to the RS1 D output. D loading. So the RS2 is the same. If RS2 is equal to the RD, then the RD in is forwarded to the RS out. Okay, then this is the normal case. It's the normal case. This is the forwarding case. So internal forwarding is already implemented in the register file. So you don't need to modify the register file, right? But you need to implement the data forwarding and hazard detection unit. Okay. So which means data, the result of the ALU or result of memory can be forwarded from the memory stage to the execution stage. So which means this one is forwarding task. Also, the write back data can be forwarded into the execution stage. Okay, so you need implement this data forwarding part. And then, as I mentioned, the data forwarding is a little bit tricky. So which means that it's a somewhat difficult part of the pipeline process of design. Okay. And then also branch unit is, as I mentioned, the branch unit is following the forwarding multiplexers. Okay, so actually this design is a little bit different from the textbook design, but it's simpler. Okay, and then also you need to implement the hazard detection unit. Okay, so hazard detection unit. So it's a data hazard. So when the data hazard is detected, which means that when the load instruction is in the EX stage, and then the following instruction, the next instruction requires the data from the load instruction, that is the data hazard. Then instruction batch and ID stages are stored. Okay, so you need to also implement this part, the data hazard detection. Okay, so if you see the skeleton code, so you can find that this is the hazard. So this is the hazard detection unit part. So as you can see, the hazard detection unit is in the ID stage. Okay, so you need to implement you need to complete this part. Also, some important part is the forwarding. Okay, and then as I mentioned, you need to implement the data forwarding from EXMEM and then mem write back. Okay. So you need to complete the actually in this part you need to implement the forwarding multiplexers, and then you need to implement the forwarding unit. It's a control unit. Okay. Then you need to prioritize forwarding conditions. So please read the comments in the skeleton code. Okay? And then also if we follow some signal flows, and then structure of the skeletal code, and then also you can just fill the blank part, okay? The fill this part for implementing this pipeline the processor, okay? Running unit, ALU, and the branch unit is here, and then this is the also you can find the execution and memory pipeline register. Okay. So just modify, just complete this pipeline on the CPU.sp. Okay. So actually, I believe the data coding part or headed decision part is the so it's somewhat a difficult part in this lab. Okay. So as I mentioned, the pipelining is very simple. The pipeline concept is very simple. We can just insert the pipeline registers between steps or stages. But this part, the hazard detection and the data forwarding is a somewhat difficult part. And then if there are some errors in this part, then we can find that the instructions generate incorrect results. Okay, and then you need to detect this incorrect output from instruction, and then you need to debug it. Okay, so this is somewhat difficult part. So please start early. So please start today. Okay, and then so even though you did not complete the single cycle processor design, don't worry. So actually, if you open the compression file, then you can find the complete single cycle processor design. It's a complete design, right? So even though you fail to implement the single cycle processor, then you can use the included single cycle CPU .scp. So this is the complete design, okay? And then you can start from the this part, okay? This is the single cycle processor design. Okay, so any questions about the lab assignment? Okay. Okay, good. And then please start today. Okay. Okay, so also I posted the homework assignment, and then in the homework assignment, so I just provide the questions. And then if you can start answer the questions by yourself, and it will be very helpful for understanding some difficult parts in pipeline architecture. Okay? So actually, I just focus on so in the question, I just select the question regarding the data forwarding or hazard detection. So the exceptions. Okay, so please try to answer the question by yourself, and then again, I believe if you can answer the question by yourself, and I believe you can understand some difficult parts in pipeline architecture. Okay, so we are learning about the memory hierarchy because so in the previous class I explained about the memory hierarchy. So why do you use memory hierarchy? Because we do not have perfect memory devices. And perfect memory device means that memory is very fast, and then memory size is very large, and then memory is very thin. So this is the perfect memory, but we do not have a perfect memory. Okay. And so actually the memory is slow. Memory is slow when the memory size is large. So we need, if we want to use the faster memory, then we need to use the smaller memory. Okay, and then also the performance of memory is determined by memory devices or memory technologies. Okay, so for example, we can use SRAM or DRAM, or we can use flash memory, but the performance of these memory technologies is different. Okay, and then also this is very important. So you need to understand the data locality. So then there are two kinds of locality. So two kinds of locality are observed in our workload. Okay, so this is the temporal locality and then spatial locality. So you need to understand the definition of the temporal locality and spatial locality. If the same data is used again and again, it's called the temporal locality. If the near data is used in the near future, then it's called spatial locality. Okay? And then because of data locality, we can use memory hierarchy. Okay? So memory hierarchy means that there are hierarchy levels, and the high level of the hierarchy, this memory is small, so it's small and fast and expensive. The low level memory, like the storage, size is large, so you can understand the size is large, and then also it's very, very slow, and it's cheap. Okay, so this is the memory. So this is also very important concept in the computer systems. So most computer systems use memory hierarchy. Okay, so actually the memory hierarchy is implemented in actually all computer systems. Also, we learned about the hit and miss in the memory hierarchy. Okay, so hit means that so in the memory hierarchy, the size of a higher level memory is small, so we cannot store all data in this high level memory, which means that if the data is requested by a processor, then the request data can be found or cannot be found. There are two cases. So if the request data is found, it's hit. If the request data is not found, it's a miss. Okay, so you need also. So this is also very important concept and also important terminology. So you need to understand hit and miss in the memory hierarchy. Okay, so let's learn about the various memory technologies. So why? So because I mentioned that actually the different levels of the memory hierarchy use the different memory technologies. Okay? So I mentioned, it's expensive, but it's cheap. Okay, so it means that the memory technologies are different. Okay. Okay, we can use various types of memory devices. So these are examples. So we can use the static RAM, it's called SRAM. Okay, so this is the most expensive memory, which means it's the fastest memory. It's a SRAM. Okay, so this is the typical latency of the SRAM devices. The latency is around the 0.5 nanosecond, but it's faster than it's faster than the 0.5 nanosecond recently. But So it's around the nanosecond latency, and then or less than nanosecond. So static memory is the fastest memory, and then also it's the most expensive memory device. Okay, so which means we can use as RAM for the higher level memory, hierarchy, higher level. So actually, we can implement the SRAM in the CPU chip, okay? Because the SRAM uses the same semiconductor technology as some CPU or some normal non-memory technology. Is a normal some CMOS technology. So usually, so we include the CPU chip includes the SRAM. So SRAM is used for the on-chip memory. On-chip memory. Also, so on-chip memory means that this is the memory inside of a chip. Okay, SRAM. And then you can use the dynamic RAM. So it's called DRAM. Right? So latency of DRAM is the tens of nanosecond, like the 50 nanoseconds to the 70 nanosecond. And then it's cheaper than SRAM. Okay, but the DRAM technology is different from the normal processor technology. Okay, so actually the DRAM is located outside of a chip. So this memory is called the external memory. Okay. Also, the DRAM is slower than SRAM. Also, another part of the DRAM is that the DRAM is the external memory. Okay, so which means that the CPU is connected to the DRAM. So this is the external memory via PCB wire. It's a PCB wires. So if the channel is implemented outside of a chip, then it's slow and it's expensive. Okay, so but it's slow. You can just think that DRAM is outside of the chip. So then we need to use the external PCB wires to connect CPU and the RAM. So it's very, very slow compared to the SRAM. But as I mentioned, SRAM is the on-chip memory. So SRAM is inside of a CPU. So SRAM. Okay. And then magnetic disk. So the hard disk drive. So actually, recently we frequently use SSD, the solid state drive, but we can use the hard disk drive, okay? Because the hard disk drive is cheaper than the SSD. So magnetic disk, so it's very, very slow. So this is the millisecond latency. So this is a nanosecond. So nano is the 10 to the power of 9 milli, 10 to the power of -3. So extremely slow. Okay, but the capacity is very large and also it's very cheap. So as I mentioned, what is the ideal memory? The access time of SRAM, fast, then capacity and cost of magnetic disk. But I mentioned that so we do not have ideal memory, but this is just the fantasy. Okay. So the memory hierarchy, the different levels of memory hierarchy use different memory technologies. Okay. Okay, let's learn about some basic of memory. So we can understand the memory like the is array of data elements. Okay, so it's a two-dimensional array of cell. So the address is given, then some data is out. Data is out. Okay, so two-dimensional means that so this is the so actually the data includes the multi-bits, the multiple bits, and when the address is given, like the address 00, then the data multiple bits of data is out from the memory for this address. So if we use the another different address, then different data indexed by this address is out from the memory. Okay, so this is the two-dimensional array of bit cell. Okay, we can store one bit data for each cell. So which means that the memory includes multiple bit cells. Okay, so this is the address, and then the number of bits for the single element is called the width of the memory, and then the number of elements in the memory is called the depth. Okay. So this is the example. So number of words is the 4. So which means that this memory includes the 4 elements. Okay. And the word size is the 3 bits. So which means that one element size is the 3 bits. So this memory includes the 4 by 3 bits. So total 12 bits. Okay. And then if the address is given, then so this address is mapped to this element. Okay. Then the data is out from the memory. So this is the very simple structure, simple example of the memory structure. Okay. So actually in the memory device, each element is called a word. Okay, this word is different from the data size word. So data size word is the 32-bit, right? So 4 byte. But when we mention a word in the memory device, the memory device, this definition of a word is different from the word that represents the size of data. Okay, so in the memory, the word represents this single element. Okay, single element that includes the multiple bits. So when the address and then the address 1 is assigned to each word. Okay, and then if this address is given, then the number of bits the number of bits is equivalent to the width of a word, so which means the number of bits in a single word. So this one word is out from the memory. So actually, we can understand the structure of memory like this. Okay. So this is the memory bit cell, the bit cell. Okay. Which means that one bit data is stored in this memory bit cell. And then word line is connected to this bit cell. And then also another part of bit cell is connected to the bit line. So which means if we want read and write a certain word okay, a certain word, then this word line is activated. So which means that the word line becomes 1. Then which means we can read or we can write data to this target word. Okay. Then we can read the data through the bit line. This is the typical structure of the memory. Okay. Then the data, the bit data is stored in this part. So like this. So address is given, then there is the address decoder, and then each line, the output of the address decoder is connected to the word line of the memory. So, for example, if the address is given, the address 1 is given, then this word line is activated, then this word, the memory cells in this target word is activated. Then, if the data is out from the pin 9, this is the read, and then that data is stored through this pin 9, this is the write. Okay, this is the behavior of the memory device. Okay. Then why did I explain this? Because I want to explain about the different structure of SRAM and DRAM. Okay. So actually the memory devices, the most memory devices have the similar structure. Okay. So the data is stored as the stored in the two-dimensional memory structure, and actually each bit is stored in this cell, right? And then we can activate the target word using the word line, and then we can read and write data through the bit line connected to the memory bit cell. Okay, this is the same for the most memory devices. Then what is different? This part is different for different memory technologies. Okay, and so which means this is the bit cell of the SRAM. Okay, so as you can see, this is the inverter, and then this is the inverter. So two inverters are connecting each other. So which means that the input, so this is the input. So this input of inverter is connected to the output of this inverter. Also output of this inverter is connected to the input of this inverter. So it is called the cross-coupled inverter. So if you took the this dynamic course, then actually this is the bistable logic. Okay, which means that we can store data. We can store data in this cross-coupled inverter. Okay. So if we use the SRAM, as this is the SRAM, the B cell of SRAM is the cross-coupled inverter, and then also we use this control logic connected to the word line. Okay, so as you can see, in the SRAM, the signal, the bit data is continuously driven by active circuit. Okay, so sometimes this is active circuit. Okay, so which means it's fast. Okay, just to remember that this is fast because this is the active circuit, and also actually the size is large because in order to implement the inverter and then this control gate, then we need to, so each inverter so requires two transistors, and then so this is the two transistors, and there will be also the additional two transistors for the control gate. So actually, in order to implement the one stair of the SRAM, then we require 6 transistors. So it is called the 6 transistors per stair. That's why the SRAM is expensive. Okay. So how about the DRAM? So this is the structure of DRAM. Okay. So this is the cell of DRAM. So then it's different, right? So DRAM is composed of one control gate here, and then this is the capacitor. Okay. So actually, one stair of DRAM requires the one transistor, per stair. So one cap. Okay. So actually, the DRAM, the data is stored in this capacitor. Okay. So, but if we just compare the SRAM and DRAM, the SRAM requires the 6 transistor per cell, and then DRAM requires 1 T per cell. So DRAM is cheaper. Okay. So as I mentioned, actually the word line and bit line structure. So the memory structure is the same for the DRAM and SRAM, but only the bit cell. This part is different. Okay. So we can compare between SRAM and DRAM. Both is expensive. DRAM is less expensive, right? Obviously, right? And then latency faster, the latency is low. So if the latency is low, which means that its memory is faster, the latency is high, that's lower density. So obviously, DRAM is higher because DRAM use the less transistors per cell. So which means capacity is high. And then placement, internal and external. So DRAM is the external memory because of this part, this capacitor part, the DRAM technology is different from the normal processor technology. Okay, that's why. So DRAM is the external memory. So actually, the DRAM is a very complicated device. Okay, so actually, DRAM is also a very complex structure. So, but in this course, I will not explain about the structure of the DRAM. Okay, but you just remember this part. So if you can compare the SRAM and DRAM, then which means we can use the SRAM device for the faster memory, and then DRAM device for the some slower memory. Okay. So I will skip this part. Okay. Part and this part. So with the advanced in semiconductor technology, the DRAM capacity is also increased, has been increased. Okay. Here. Also, another type of memory is the flash memory. So flash memory is the non-volatile memory. So what is the volatile and what is the non-volatile? So volatile. The volatile memory means that the data is erased if the power is off. The power is disconnected from the memory device. Then the data is removed or erased. This is the volatile memory. In Korean, the 휘발성 memory. volatile, 날아간다, 휘발. Okay. Then what is non-volatile? So it's a non-volatile. So this is it's not volatile, which means even though the power is off, the memory device, the data is kept. Data is not erased. Data is kept. So flash memory is the non-volatile memory. So which means that we can use flash memory as the storage device. Okay. But flash memory is much slower than the DRAM. Okay. So really, so in this slide, the DRAM latency is the tens nanosecond, and then the flash memory latency is the tens microsecond. Okay? Tens microsecond. Okay, micro is the 10 to the power of 6 minus 6, not 6. Okay, so in this slide, you can find that it's 100 and 1,000 times faster than disk. So it means the magnetic disk, but it's slower, much slower than the DRAM. And then also the flash memory is the non-volatile memory. Okay, but the density is also high. That's why we use flash memory as the storage devices, storage medium. Okay. So then actually the flash instead is why is it called flash memory? So you know flash is some flash in the bubble, okay? So that is heat very fast, right? So flash actually it means the very fast, okay? But it means it's faster than magnetic disk. You know the flash is the very fast man in the Marvel universe, right? Okay, so we can use this flash memory as the storage device. And there are some also. But in the traditional computer systems, we use magnetic disk. Okay, so and then unlike the other memory devices like the DRAM as well or flash memory, so this magnetic disk is the mechanical drive, mechanical system. So which means that we have motor. Okay, it's a mechanical drive. So which means that the motor rotates is flatter is a one bar flatter, and then actually the data is stored in the surface of the platter. Okay, but the mechanical device is actually very slow because it's mechanical. Okay, so the flash memory is the solid state drive, solid state memory. So which means that unlike the other memory devices, the address is given and we can read data. The address is given, we can write data with the electric signals. But hard disk drive is different. So actually, in order to read and write data to the hard disk drive, then we need to rotate the platter with the motor. So it's extremely slow, extremely. Okay. So just ignore this, and then just this number. So what is the average read time for this example? Is the millisecond. Okay, so if we use the 1 gigahertz CPU, then clock period is the 1 nanosecond, and then 6.2 milliseconds. So this is the 10 to the power minus 3, and then nanosecond is the 10 to the minus 9, 10 to the power 9. Then 6.2 milliseconds is the 6.2 multiplied by 10 to the power of 6 cycles. Okay, so 1 gigahertz CPU. Okay, so which means if the data is in the magnetic disk, then and then if a certain program requires the data in the magnetic disk, then if in order to read this data, then the CPU needs to wait for 6.2 multiplied by 10 to the power of 6 cycles. Very large number. Okay, so it's extremely slow. So I hope you can understand some various technologies, various memory technologies. So then why did I explain this? So here. So I mentioned that we use the different memory technologies in the different levels of memory hierarchy, right? So as you can see, this register file we use as well, because register file is inside of a CPU chip. Cache, we do not learn about the cache here, but we use SRAM, but the size is larger. So that's why the cache is slower than the register file. So it is the same technology to use, but the cache size is larger, so that's why the cache is slower than the register file. This is the cache and register file is included in the CPU chip. So this is the on-chip memory. DRAM is the external memory. This is DRAM, right? And then for the main memory, we use the DRAM. Okay. So DRAM is faster than the flash memory or magnetic disk, but it's slower than SRAM. Okay, but as I mentioned, the DRAM is less expensive than the flash, less expensive than SRAM. Okay, then we can use the flash memory or magnetic disk for the storage. So it's extremely slow. Okay, so I hope you can understand the different memory, the characteristics of different memory technologies, and this different type of memory devices are used for different levels of memory hierarchy. Then we can understand why cache is required. Okay, so the basic of caches is just 5 minutes. So what is a cache? So actually, I believe you can understand. So, so this is the new terminology, cache. Okay, then what is a cache? So this is the definition of cache. So actually, the normal definition of cache is the hiding place. Okay. So in Korean, the cache means that is the kind of 비밀 금고, so it's a hiding place for some secret money. Okay. So actually, that is the normal meaning of cache. But we are learning about the computer architecture, and so we need focus on its meaning. So what is the cache? So as you can see, in the computer, cache is a temporary. So actually it's a temporary space, temporary storage space or memory for what? That allows fast access to data. So in a computer system, this storage or this space is called a cache. Okay. So also we can search for the definition of cache in Wikipedia. Okay. Then the computing, right? So in computing of cache, okay, is a hardware or software component, but we are focusing on the hardware because this is the memory system. Then stores the data. Okay, but you need to remember that this is the temporary space. Also, the programmers, the software programmers actually do not know about the cache. What does that mean? In chapter 2, when the instruction is given, then instruction can change register file, right? And memory. So this memory is the main memory. So it's DRAM. The main memory. Also PC can change it. PC is also kind of a register file, register. So actually, these memories, register file and the main memory and then program counter is revealed to the software engineer. Okay, that means that the software can understand the number of register file and then the main memory and then PC. Here is the cache. So I frequently use the $sign for the cache because the pronunciation is the same. So cache is the pronunciation of cache is the same to the cache $sign. So I frequently use the cache. Where is the cache? Cache is not here. It means that the cache is managed by hardware, not software. Okay, and then cache. Actually, the software engineers do not know about the cache, but this cache is only used for fast access, fast data access. So only used for higher performance. Okay, and then you need to remember that cache is automatically managed by hardware. Okay, so this is a cache. So the next class, so we will learn about the cache. Okay. Any question? Okay, thank you for your attention. See you in the next class. Then keep hands.